Hello everyone, welcome to the video lecture series on manufacturing processes. I am Kishore, Assistant Professor in the Department of Mechanical Engineering, MLR Institute of Technology, Hyderabad. We will start with what we have already discussed in the last lecture, and then we will see what we are going to discuss today. So, last lecture we discussed what are the terminologies, what are the terms that generally used in casting. Then we saw what is the importance, why do we use gating system. Then after that, also two parts of the gating system we have seen how to design these two. First one was pouring basin and second one was a screw. Today we will discuss about the importance of pouring, why do we need pouring and what is the importance of pouring. Then we see how many types of gating systems are there, means different types of gates, and then we will see how to calculate the pouring time. So basically there are three types of this gating, I mean three ways through which metal can enter inside the mold cavity. First one is known as top gate, that is also known as vertical gating. So it's all about the positioning of the gate, where it is. So this is the mold cavity. So we can see that this gate is positioned at the top of the mold cavity. That's why this is known as top gate. Second one is bottom gating. So you can see here the gate is positioned at the bottom of this mold cavity, or we can say in the drag portion. So this is known as bottom gate. And the third one is this gate is placed at the intermediate of the mold cavity. So this is known as parting line gating. So all these three have their advantages and disadvantages, and accordingly, depending upon what kind of material we are going to cast, we will use this different gating system. Okay, so first one is top gate. This is also known as vertical gating. So what happens in this one, if this gate is placed on the top of this vertical mold cavity, so metal will come inside the mold cavity because of gravity. So it will fall through a distance. Suppose something is coming from a distance, so it will have potential energy. So whatever potential energy will be there, here in the liquid, that potential energy is there. So it will fall through a distance, and once it will fall through a distance, it will have kinetic energy. So with this kinetic energy, it will come and strike the bottom of this mold cavity. So the chances is very high that it will exert the high amount of force over there. Because of that, erosion may happen over there. Another thing is turbulence is also very difficult to eradicate in this case. So in top gating system, these two are the main problem. Another problem is the liquid coming out from the gate generally is open to the atmosphere, and if it is open to the atmosphere, it is having very high temperature. So chances of oxidation is also very high. But these two things are not there in the bottom gating. So what is happening here, this gate or the point through which liquid is entering in the mold cavity, it is at the bottom of the mold cavity. So slowly this is filling the mold cavity. Slowly metal is going up and it is filling the mold cavity. So here we can see metal is not falling through because of the gravity. So it will not exert high amount of force on the mold cavity. So chances of erosion and turbulence is almost negligible in this case. But the problem with this one is here directional solidification is very difficult to achieve. And another problem is pouring time will be very less, because at the liquid metal will fill inside this mold cavity, this velocity at the gate will start to reduce. So it will take more time to fill this one. Okay, and the last one is the parting. So you can see here the gate is positioned in between this cope and drag, and this is also large. This horizontal section is additionally large. This ensures that the metal distribution inside the mold cavity is uniform. So generally it is used, and also the chances of turbulence is very less in this case. So now after this we will see how to calculate the pouring time. Pouring time is very important. We need to understand what is the meaning of pouring time. In this diagram we can see this is a top gating or vertical gating. Okay, so we can see this is the pouring basin. Means liquid will be poured from this one. This is the pouring basin. So suppose liquid inside this one up to this particular height. This is the sprue. So this liquid is coming, and this is the mold cavity. So what is the meaning of pouring time? The meaning of pouring time is how much time liquid is taking to fill completely this mold cavity. This is known as pouring time. So this diagram is for vertical or the top gating system. So we are going to calculate how much time it will take to completely fill the mold cavity. So we will take some notations. This area of cross section we are taking AG, that is area of cross section of the gate, and this height from here to here, suppose we are taking HP, means height of the pouring basin. Okay, and suppose we are assuming that the liquid inside this one at a particular time is filled up to height H. Okay, so if we apply the continuity equation, so we know continuity equation, whatever the volume with time is coming out from this one and going inside this mold cavity will remain constant. So if we will write volume with respect to time at this position, so what it will be? It will be simply area of cross section AG into what is the velocity over there. Suppose we are taking with what velocity is coming is Vg, that will be equal to area of this mold cavity. So suppose we are taking area of this mold cavity as AM, so this will be equal to area of this mold cavity AM into, suppose this height is H. So as this height is changing, so this is not constant, so it is varying with respect to time, so we can differentiate this with respect to time. As this is constant area of the mold, so we can take this out, so it will be AM and this will be simply dH upon dt, and this dH upon dt is nothing but time with which this mold cavity is filling over there. So we can say that also this is a velocity. So simply area into velocity is constant, that we know from the continuity equation. This equation we can write, if we will change this one, so we can write dt. If we are taking this one left side, so we can write dt is equal to simply AM upon AG into this expression we can write dH, and this we can write as Vg. So these three terms, that is AM, area of the mold cavity, and area of the gate, and this velocity of the gate, all three are independent from this H, because H is not dependent on this one. We assume that area of the mold is constant, we can see from the diagram also, but it is not necessary always it will be constant. If conical shape is there, in that case this mold cavity area, cross sectional area will not remain constant. But here in this case we are assuming that the cross sectional area of this mold cavity is constant, that is AM is constant. So all these three terms are actually constant, which is not dependent upon H. So what we can write, this dt is equal to, simply we can write AM upon this AG, area of the gate, 1 upon this Vg, velocity of the gate, into dH. If we integrate this one from 0 to t, means 0 we are taking at the starting time and t we are taking the time when this mold cavity is filled up to height H, means 0 to H. So we can see from this here that this t, that is filling time, mold filling time, or this pouring time, is equal to area of the mold, that is AM, upon AG, area of the gate, and this will be equal to this H upon this Vg, that is velocity of the gate. This is actually Vg. Now the question is how to calculate this Vg. So simply this filling time is T is equal to area of the mold, this mold area, upon area of this gate, this cross sectional area, into what is the height up to which this mold cavity has been filled, that is a small h, and this velocity of Vg, with what velocity is it coming down. So to calculate this Vg, it's very easy to calculate this Vg. Many methods are there, but as we are assuming that this part is very large as compared to this one, we can see here also. So velocity with which it is, this liquid is coming down in this pouring basin is very small. Or in other word also we can tell that the liquid level inside this pouring basin is almost constant. Okay, so we can easily calculate this one. If this is, it will become like a free fall. So if a body is falling from a particular height, it's a free fall. We know if it will fall through a height h, so after falling through the height h, once it will reach at its end position, its velocity will be under root 2gh. That is very simple. We know from simple mechanics that we can calculate like that. But in this case we can apply Bernoulli's equation also. Suppose this open section we are taking at section 1 and this one we are taking at 2, and if we are applying Bernoulli's equation at position 1 and 2, so we can easily calculate this one. So applying Bernoulli's equation applying Bernoulli's equation at section 1 and 2, we can write equation P naught, that it is atmospheric pressure upon density into acceleration due to gravity, plus velocity at section 1 v1 square upon twice g, plus whatever the height is. This height we can see, if we are taking this reference, this is the reference line. So this height we can see, this is HP actually. So we can write here HP. This is equal to, here pressure is also atmospheric. So this is this one plus V2 square upon twice G, plus it is at datum. So this is 0. So this one will be cancelled out, and this V1 velocity is very less. As I told at the starting, we are assuming that the liquid level inside the pouring basin is almost constant. Okay, so this is HP, and this V2 is nothing but VG. So we can write this one as VG square upon twice G. So from here we can write VG is equal to under root 2G, and this is HP. So this velocity with which liquid is coming from the gate is this one. So finally we can write this time, pouring time or the filling time in the case of top gating system is AM, area of the mold, upon area of the gate into this height H, that is height of the liquid in the mold cavity, upon this velocity Vg means 2G, and this is HP. So this is the filling time in the case of, top gating system. But before reaching to this one, we have assumed some assumptions are there, and what are those assumptions? We have assumed in this one that the liquid level in this pouring basin is almost constant. What does it mean? It means that the velocity with which this liquid is coming down inside this one is very, very small. It is almost 0. That is the first assumption, and we have applied Bernoulli's equation in ideal case. Ideal case means we are assuming that there is no loss over there. Okay, na? So frictional losses or whatever kind of losses over there, we are simply assuming that it is 0 over there. So on the basis of that, we have come to this relation that the filling time, that is T, or the pouring time which the liquid will take to completely fill the mold cavity, will be area of the mold cavity, which we have also assumed constant, okay, upon area of the gate through which liquid is coming, times height of the liquid in the mold cavity upon under root 2G, and what is the height of the gate and from the open face, means from the pouring basin. So this is the formula for top gating system. Now we will derive relation for bottom gating system. So this is the bottom gating system. We will derive relation how to get the pouring time in the case of this bottom gating system. Okay, so we can see here liquid is coming inside in this one from the bottom. So we will also give the notations for all the parameters in this one also. We are assuming that this is the liquid inside this one and it is going inside that, and at a particular time the liquid is up to height H in this one. Just like the top gating system, we are assuming this height is also H, and this height from this one to this height at this section is, we are taking HP. Okay, and the area at this section where the liquid is entering in the mold cavity, we are taking AG, and the area of cross section of this mold cavity we are taking AM. This height is HP, and same assumption also we are taking here, that the liquid level inside this pouring basin is not changing, it is almost same, or indirectly we can tell that the velocity with which this liquid is coming down in this pouring basin is almost 0. But the important thing to see here in this case, this area of the gate through which liquid is going inside the mold cavity is not open, means it is not open to the atmosphere. So here pressure is not atmospheric, it is different. Okay, but here as it is open to the atmosphere, so pressure is constant. The same continuity equation we can apply here also. So if you are applying continuity equation, continuity equation. From continuity equation, we can write area of the gate and velocity at the gate. This will be equal to area at the mold cavity and same dH upon dt, with what velocity or with what rate this height is changing there in mold cavity. So we can write here this expression quite easily. We can write this expression. This is if we take this t in this, so we can write dt is equal to am upon az, and this velocity we can write dt is equal to am upon az into this velocity will come, so 1 upon az, and this is dh. But interesting thing in this expression is we will have to be careful here. This dh is not independent of this az, it is dependent on the gate velocity. Okay, why this is? You can see here, if liquid is coming inside this one, we can see here when there was no liquid in this mold cavity, this velocity az will be, this velocity at this one, that is vz, will be very high. But as liquid is coming and filling this mold cavity, slowly it will start to decrease. So it is not free from this dh, which is the height of the liquid inside the mold cavity. This is not independent from the velocity of this vg, velocity of liquid at the gate position. So what we will have to do, we will have to find out what is the relation, means how to convert this vg in terms of h, so that we can solve this particular expression. So first what we will do, first we will try to bring this expression. With this expression we can write simply am upon az, and we can write dh upon this vg. Okay, so if we want to find out the time t, means we will have to integrate this expression. So what we will have to do, our first effort will be to just bring this vg in terms of h, so that we can integrate this expression easily. So first what we will do, in terms of, first we will write the Bernoulli's equation and we will try to find out the relation between these two, and we will see how to find out this velocity vg. Okay, so what we can do, we are taking this section at 1 and we are taking this section at 2. So we are writing Bernoulli's equation at these 2 points. So what we can write, if we are writing a bit between these and these 2 points, so we can write from Bernoulli's equation at 1 and 2, we can write, what we can write, P naught, here its pressure is atmospheric, so P naught rho into g plus velocity v1 square upon twice g plus what is the height, that is hp. We can write this hp, and this is equal to what it will be, this will be equal to velocity pressure at this section, that is P2. It is not atmospheric pressure, it is not open to the atmosphere, so P2 upon rho g plus velocity, that is v2 square, and v2 is nothing but velocity at this gate opening, so it will be vg actually, so vg square upon twice g plus, we are taking this reference, so here it will be, this one will be 0. So what will happen here, this term is 0, there is no problem in this one, but here the problem is this P2, how to find out this value of P2. So we can find out the value of P2. We can see here, this is just like a hydrostatic condition. This liquid is in a container. If we assume this was a container and this height is h, so what will be pressure here? This is atmospheric pressure because this is open to the atmosphere. So if we write, we can write simply P2 is equal to this P naught atmospheric pressure plus rho gh. Okay, we can write this one, just see this diagram. So at pressure at this point, we can write this atmospheric pressure plus whatever pressure this liquid is exerting at the bottom. Okay, so we can write this expression P naught plus rho gh. What we are doing here, we are dividing by rho g throughout, so we can write P2 upon rho g is equal to P naught plus rho g plus h. So this value of P2 upon rho g, if we are putting in this expression, so finally give some name to this one. Suppose this is expression 1, we are writing 1. So we will put this value putting this value in equation 1, what we can write, that what is the expression? This expression is P naught upon rho g, P naught upon rho g plus HP, P naught upon rho g plus HP is equal to P2 upon rho g, and for P2 we can write this P naught upon rho g plus H plus Vg square upon twice g, and yeah, that's it, I think. Yeah, and then it is 0. So we can see this will be cancelled out. Okay, so from here we can write Vg, simply Vg will comes out, this Vg is equal to Vg square is equal to 2g into this Hp minus H. Okay, this is the expression for Vg. Okay, now this expression we can simply put here. So we can see in this expression, this Vg is, this is constant, and this is H and this is Hp. These two are variable which is in the term of height. So now this Vg is only function of the height, that is H. That expression, if we are putting this one, so easily this expression we can integrate. So finally we can write this one. What we can write, if we are writing this one, so we can simply write this dt, if we are segregating this term, so we can write dt is equal to area of the mold upon area of the gate into this was dh upon Vg, and that was the expression. So finally we can write this area of the mold upon area of the gate, and this expression we can write simply this dh, and expression for Vg is twice g in bracket Hp minus this H. So this is dt. Suppose we are integrating this one 0 to t, and this one we are integrating from 0 to h. Okay, so once we will integrate this one, the final result for time will comes out. We can integrate this one, there is no problem, but if I am just writing the final result, but we will get this filling time, this t will comes out area of the mold upon area of the gate in the this is, and this is twice, this can be integrated, and finally this result will come integration Hp minus H minus this is under root Hp divided by this under root twice g. So this is the final expression we will get in the case of bottom gating system. So what is the time, filling time here in this case is that T is equal to area of the mold upon area of the gate, in bracket it will be twice this HP means height of the gate from the top of the pouring basin minus H, that is the height in the height of the liquid in the mold cavity, minus this height of again the gate from the pouring basin top upon twice under root twice g. So this is the final expression. So these are the two expressions. So this is all for this today's lecture. We will next see, come with some numerical based on this, and then we will come to the next topic of this gating system. Thank you.